Hey everybody, welcome back to chemistry. And so what I wanted to do was go over a particular problem on your Achieve assignment in chapter 11. And this problem is about molecular orbital theory, and this is a little bit more complicated than we've been dealing with in class. So if I can sort of blow up the screen, we'll take a look at it right now. So this is a problem having to do with trying to figure out the correct molecular orbitals and the electron configuration for a molecule where you have hydrogen bound to fluorine. So this is a little bit different than what we've been doing before. So what we've been doing before is we've been looking at two atoms of the same element bound together. And so those are called homonuclear molecules. And here what we're looking at is two different elements bound together, and these are called heteronuclear molecules. And so HF is a heteronuclear molecule, and so we're going to, again, try to figure out its molecular orbitals and its electron configuration. So the problem reads as follows. The molecular orbital diagram of HF looks different than most other diatomic species because the electronegativity difference between hydrogen and fluorine is so large. The 1s atomic orbital of hydrogen interacts with just one of the 2p atomic orbitals of fluorine to form a bonding sigma molecular orbital and an antibonding sigma star molecular orbital. This leaves the 2s and the 2p orbitals of fluorine as non-bonding orbitals. Construct the molecular orbital diagram for HF and determine the bond order of the molecule. So let me make that slide small now, and let me go to the board and solve the problem. So the first thing I want to do is, before we look at the HF molecule, let's look at a previous example that we're familiar with, which is the F2 molecule. That is good to do because I will figure out what the electron configuration of the F2 molecule is, and then I'll do the HF molecule. And I think the differences that you'll see between the HF molecule and the F2 molecule will help you understand the molecular orbitals and the electron configuration of the HF molecule. So just to get oriented here, here we have the electron configuration of a single fluorine atom. So fluorine has 9 electrons, and there are 2 electrons in 1s, 2 electrons in 2s, and 5 electrons in 2p. So again, first off, let's just imagine how 2 fluorine atoms form molecular orbitals to form the diatomic fluorine molecule. So on the left side here, we have 1 fluorine atom's atomic orbitals, and so here I'm just writing them out in terms of increasing energy. And then on the right side, we have the other fluorine atoms, and we're just writing out their atomic orbitals increasing energy as well. Now, what I've done is I've kind of mapped out what these molecular orbitals that will be formed from these atomic orbitals are. So let's go ahead and fill them in with electrons to figure out diatomic fluorine's electron configuration. So I think you already know how to do this, and so the way we've been doing it before is here we're looking at all of the orbitals. That includes the core orbitals and the valence orbitals, and therefore we want to add up all the electrons of fluorine. So here we have 1 fluorine, which is 9 electrons. The other fluorine is 9 electrons. So we want to put in 18 electrons in this configuration. And I could go ahead and do that, but let me do it in a slightly different way. So another way, as you probably know, that you can figure out configuration for a molecule is just if you have mapped out where the electrons are in the atomic orbitals, you can sort of use that information to figure out where they go into the molecular orbitals. So let me just go ahead and do that. So we're starting out with the molecular orbitals that are formed from the 1s atomic orbitals. And I think you know a pair will go into the bonding molecular orbital, which is in the first energy level, and another pair will go into the antibonding orbital. And so the same thing happens here when you're now in the second energy level. Same deal. The electrons are no longer found in atomic orbitals in F2. Instead, those electrons are going to be found in a bonding orbital in the second energy level and an antibody orbital in the second energy level, which I designated there. Okay, so next, let's talk about where these electrons that were in the 2p sublevels go. What molecular orbitals do they go into F2? And you can see that that's a more complicated pattern, but I think you can sort of figure out what to do here. So you have 5 electrons in this fluorine's 2p, 5 electrons in the other fluorine's 2p, a total of 10 electrons. So let's fill in this molecular orbital pattern with 10 electrons here. So here we go. So erase these, there we go. Okay, 10 electrons, here we go. 2, 6, 8, 10. And so that is diatomic fluorine's electron configuration. Okay, so you see now how we get the molecular orbitals for diatomic fluorine and how we can figure out its electron configuration. Now what we're going to do is change things. So what I want to do here is we are going to figure out what the molecular orbitals that form are for HF. So what I need to do is I need to remove, say, one of these fluorine atoms here, and I'll just remove the left one here. So we're going to quickly remove the left fluorine like this. And also I'm going to get rid of these electrons here. And like this. Now, we're going to replace a fluorine with a hydrogen, okay? So now we have hydrogen instead. And as you know, hydrogen has one electron. So now what we're going to do is figure out the molecular orbitals, not for diatomic fluorine, but for HF. Okay, so let's talk about what those are. So this is for HF. So let's figure out what the molecular orbitals are for HF. And so one thing I think you can sort of immediately see is that we have far fewer orbitals for hydrogen than we do for fluorine, right? And so let me go ahead and draw on where the hydrogen orbital is. So you may recall from our beginning discussion of valence bonds that form between simple molecules that one way you can model HF is using valence bond theory. And so valence bond theory kind of predicted that hydrogen, with its single orbital, it has a 1s orbital here and has one electron, would form a bond with fluorine, so where the 1s orbital would overlap with fluorine's 2 p orbitals, and you would find the 2 electrons there. So this kind of implied that where the 1s orbital is found in the molecule, it's in such a place that it can pair up easily with one of fluorine's p orbitals. So going back to this picture here, where do I put in the single hydrogen 1s orbital? I'm going to put it close to fluorine's 2 p orbitals. And so also I'm going to put it a little higher than normal. So I'm going to put it here and put it a little higher than normal here. And so we're going to write 1s. So you might ask a question as to why did I put the 1s orbital a little bit higher than normal? And the reason is because with molecular orbital theory, when you're writing out diagrams, what they like to do is if you have 2 atoms of the same electronegativity, they put the atomic orbitals at the same level because they're at the same energy. On the other hand, if you have 2 atoms with a different electronegativity, then they put the atoms at different levels because they have different energy. So hydrogen's 1s orbital, when it forms molecular orbitals with the 2p orbitals in HF, it has a slightly higher energy than just say hydrogen's 1s orbital by itself. Okay, so we've got that done. So the next thing we're going to do is we're going to put in electrons here into these orbitals. So hydrogen gets 1 electron, and fluorine gets its 9 electrons like this. So nothing unusual here. So now what happens is we have to predict the molecular orbitals that form between hydrogen and fluorine. So this is going to be a little bit different. And so here's where the picture is really different. So you can see that before, when we had another fluorine bound, we had a 1s orbital that had the same energy as the 1s orbital of the other fluorine, and we could form these molecular orbitals. But now you can see hydrogen's 1s orbital has a lot higher energy, and it cannot form molecular orbitals with the 1s orbital here from this fluorine. So here, this system of molecular orbitals does not form. So I'm going to have to erase this. Instead, something else happens. What happens is that basically because we cannot form molecular orbitals between this fluorine and another atom, this 1s orbital is unchanged. So this 1s orbital is still there in the molecule. So to indicate that, I'm just going to indicate that this is in the molecule here, and this is 1s like that. And so that orbital is basically unchanged, and this pair of electrons now is part of the 1s orbital in the molecule. Okay, similar deal with here, the molecular orbitals that form maybe from hydrogen and fluorine in the second energy level. There aren't any that formed. And the reason is because although there is a 2s atomic orbital for fluorine, there is no 2s orbital for hydrogen. So these system of molecular orbitals just does not form. And so instead what happens is that in the HF molecule, fluorine's 2s atomic orbital is retained. So I'm going to write that there now in pink to indicate it's in the molecule. And so that's still there with its 2 electrons. So we're going to indicate that. Okay. Now here's where it gets a little bit interesting. So you do have molecular orbitals that will form between the hydrogen 1s atomic orbital and one of the 2 p orbitals. Now, so how are we going to draw that out? So it kind of looks like this. So you can see that of these 2p orbitals of fluorine, one of them has a single unpaired electron. The 1s of the hydrogen also has a single unpaired electron. And so from those atomic orbitals, you will get only 2 molecular orbitals that form. And one will be a sigma orbital and one will be a sigma pi orbital. So what will happen is you'll get a sigma orbital here. It'll have some kind of name. I'm not sure what it is. We'll just leave it as sigma. And then here we're going to have here a sigma pi orbital here. And so this forms from the hydrogen and the fluorine like this. Okay, so the question is, it forms from these 2 orbitals, right? What happens to these other 2p orbitals that are here? Well, the other 2p orbitals, as you might expect, they do not change. And so what I'm going to do is redraw the 2p orbitals here, like that. Okay, so these 2p orbitals here are now here. So now what we can do is fill in this picture with the electrons. And so what you can see is that from the bonding and antibody molecular orbitals that form between hydrogen and 2p of fluorine, what I'm going to do is pull off those electrons there. And so they will go into the lowest energy molecular orbital that's available to it. So they should go into the sigma orbital. Then we have 2p atomic orbitals in fluorine that remain intact in the molecule. So they're there, and so we're going to put electrons here, like that. All right, now I want to get into some vocabulary really quick, in that you know that when you have a pair of atomic orbitals form 2 molecular orbitals, the lowest energy one is called a bonding orbital, and then the highest energy one is called an antibonding orbital. Now, what do you call atomic orbitals that are part of the molecule but are not molecular orbitals? We have several of those here, right? So here in the HF molecule, we have a 1s atomic orbital that was never turned into a molecular orbital. We have a 2s atomic orbital that was never turned into a molecular orbital. And then also we had 2p atomic orbitals of fluorine that never became molecular orbitals. Those atomic orbitals that never become molecular orbitals are called non-bonding orbitals. And so to indicate that, I'm just going to write NB here beside the orbital. This is a non-bonding orbital. This one also is a non-bonding orbital. And then these 2p orbitals here are also non-bonding orbitals. Okay, so this is the correct configuration of the HF molecule. And so you should be able to answer your question on the achieve. And so as I recall, or I can see it on the screen there, the achieve does not include the 1s non-bonding orbital, but you can see that you're going to have to fit in a pair of electrons into the 2s non-bonding orbital, and then you're going to have to fit another pair for each of these two non-bonding orbitals that form from the two p orbitals. And then I think what you're going to see is that you have another pair of electrons here, one that came from hydrogen's 1s orbital, one that came from fluorine's 2p orbital. So we have a pair of electrons in this lowest energy molecular orbital here, and we have no electrons in the higher energy antibonding molecular orbital. So how do you figure out the bond order of the HF molecule? Well, the formula used to figure that out is exactly the same as the one you've been using before. So let me write that out. That bond order is equal to 1/2 the number of bonding electrons in bonding orbitals minus the number of antibonding electrons in antibonding orbitals. Now, you will notice here that we have some electrons here that are in non-bonding orbitals. But look, this formula you use has no term for non-bonding electrons. So you do not put non-bonding electrons into this formula. You only put in the number of electrons you see in bonding orbitals and antibonding orbitals. Okay, so let's find those. All right. So here we have some electrons in this 1s non-bonding orbital. So non-bonding is not part of the equation, so we ignore those. We have some electrons here in the 2s non-bonding orbital. Again, we ignore those. And then we have 4 electrons in 2p non-bonding orbitals. We ignore those. However, you see that we have 2 electrons in a bonding orbital that form between H and F, and we have no electrons in the antibonding orbital that forms between H and F. So here it's just going to be 1/2 bonding electrons, which is 2, minus antibonding electrons, which is 0. So the bond order for the HF molecule should be 1. Okay, thank you for listening to that. We'll see you next time.